Hello, everyone. Good morning, and welcome to my talk. Feel free to join us. I was about ready to start. Let's start with some introductions. Oh, sorry. My name is Berwout of Vries Robles, which is kind of difficult to pronounce in any other language than my own. I work for Info Support. We're a software consulting firm. We make awesome sauce, and we also do projects for customers all over the Netherlands, basically. I work for a department called the Professional Development Center, and it helps with project startup. So when a project starts, they come to me, and I help them select their dev tools and get started with their CI/CD pipelines, basically. So anything Jenkins, and I'm usually your guy. That's not what this talk is about, though. Topics I'm going to cover. We're going to start with a little bit of history of HTTP. Why did we need HTTP2? And then we're going to look at how we can use it. And then how we can use it with reactive streams. Funny, there's a small demo first that basically is my first, how do I get started with reactive streams with Spring WebFlux. And then there's a larger demo where you're going to need your phones. You're going to need your sound as well, which is going to be interesting because some of you might get called. And finally, we're going to look at what the future looks like with HTTP3. All right, so starting with the history. It started in about 1990-91. It was a one-line protocol invented by Tim Berners-Lee, and he wanted to get a response from a server, basically. It was very simple. It was designed for HTML documents only, and it was request-to-response. So we'd send a request to the server, you would get a response back, and it would close. It looked something like this. You would do a get to a resource, and you would receive a very simple HTML-only response. If only life were still that simple. Then HTTP 1.0 came along. About 1991 is when they started development on that. Browsers emerged around 1994, which is the first time we could actually view HTML document nicely. There were a bunch of different implementations for HTTP 1.0 because it was never an official spec, so everybody was kind of just doing their own thing, and it wasn't sure if your HTML was being rendered one way in one browser or one way in another browser. So they started the HTTP working group to combat that, to make one standard, basically. And in 1996, they published the first document which documents the usage of HTTP 1.0. It wasn't anything like a standard, but it was more like, this is what most of the companies are doing, and this is probably what you should be doing as well. It kind of looked like that before we had browsers, so not very exciting. Then some features of note in the HTTP 1.0 protocol. You had request and response headers for the first time, so you could pass some metadata to your request, which is nice. You got a status, whether it failed or whether it succeeded, or maybe even why. You had some content types, which is actually the birth of the internet, because now we could send pictures. Very nice. An HTTP 1.0 request looked kind of like this. You had a verb, which described what you wanted to do. Then you had a resource identifier, which is the same as where you're going to get the resource. You had a version for the first time, because we had 2 versions now. They thought about that. You had some headers, basically some metadata about the request. Who's it from? What kind of stuff do I accept? You had a blank line separating the headers from the body. And then you had any request body. Still fairly simple. Then a response, which looked like this. We had a status line with obviously a status code. So now we noticed our request succeeded, which is very nice. Some headers, a blank line, and a body. Most of you hopefully are familiar with this. Then it's in use from about 1995 to current age. It says current because there was a publication even in 2014 still on the HTTP 1.1 spec. And last time I gave this talk was half a year ago, and about 28% of the top 10 million websites were using HTTP2, and the rest was using HTTP 1.1. And now it's about 36%, so we've gained 8% in the half year, which is kind of nice, but it's still majorly used everywhere, actually. It's the first formal standard by the IETF, so they published a document which standardized the usage, said this is what you have to do, this is what you have to implement. Some features of note in HTTP 1.1. They figured out that sending a request and receiving a response and then terminating the TCP connection was not very efficient, so they made something called Keep Alive, which keeps your request alive for 30 seconds and allows you to send multiple HTTP requests over the same TCP connection. And they made it default, so it actually backported into HTTP 1.0 as well. Then chunked encoding, which was a way for you to send large files in chunks, because when the TCP layer, they already chunk up your packets. And when they arrive on your side, your layer reassembles them and sends them back up to your application layer. But with chunked encoding, you were allowed to take chunks of that data and pass it up to the application layer. So if you ever saw a picture load very slowly, line before line, that's your chunks of data being passed upwards before you actually had the full response. So before that, you had to wait for the entire picture to get sent to your layer, and then you would receive the full picture, which wasn't very nice because you would be staring at a page for 30 seconds and it wouldn't load. Well, we had cookies, which was the first time we could store state about the user, which was very nice. We could store logins, store whatever they bought. Kind of less used now because of all the annoying cookie laws, but it was an important feature. So we had these features which allowed us to have basically the internet. But what is the problem that we were facing? There was an extreme growth in devices. Not just your servers and your computers were connected to the internet anymore, but it was also your phones, your fridges, your ovens maybe. Everything started connecting to the internet, so there was an extreme growth in devices. Responsiveness became more of a thing when Google and Facebook started making pages that loaded in 200 milliseconds or less. Your users would stop using your page if it loaded any slower than that, basically. It didn't have any real support for high volumes of data, and it didn't have any support for the server to send you anything without you asking for it. There were a few solutions to responsiveness that we had in the past. Polling was the first one. It's kind of like you're trying to make a web page responsive by calling the server over and over. It's like your friend Paul standing in the kitchen. He can't see the football game that's on TV, but he keeps asking, what's the score? And what's the score now? And what's the score now? And what's the score now? And then when someone scores, he knows immediately. You can imagine it's kind of annoying to have that friend Paul. So we invented long polling, which was basically Paul would go to the kitchen and he would say, well, whenever they score, just tell me. And then whenever they scored, you'd have to tell them. There was a problem with that, is that you had to remember that Paul asked you to give him the score. And we only had a limited number of HTTP connections, and it would hold up one of your HTTP connections. So you could arrive in a state where you had like 6 of these long polling requests going, and you couldn't do any other requests, which is not very nice. Then we invented WebSockets, which was a way of saying, well, let's ditch the whole HTTP protocol. I'm going to take your connection now, and I'm just going to stream binary data over it. And the nice thing about WebSockets was that it went both ways. So the server could also send you data, but the annoying thing was it wasn't HTTP, so a lot of web servers had trouble with it. A lot of firewalls had trouble with it. And there was no protocol at first, but now there are plenty of libraries supporting all sorts of protocols for WebSockets as well. Then you had server-sent events. They were kind of smart. They were like the long polling requests. You would open a request to the server, and he would send you data, but he would send you data with chunked encoding, which was meant for those large files I told you about earlier, but we abused it for server-sent events to basically send you a small chunk, and then another small chunk, and then another small chunk, and we just kept our request open, and the server would be able to send us events. But like with long polling, we had the same drawback, which is you had to keep the request open all the time, and we only had a limited number of those. So along came HTTP2 to try and solve some of those problems. Development started somewhere in 2012 and is still ongoing. It was publicized in 2015, and actually Google sort of started experimenting with this protocol called Speedy, which they implemented in their browser. And it's HTTP2 started as a copy of Speedy, and then the HTTP working group had Facebook review it as well. And that's basically how HTTP2 was made. It it was a binary protocol for the first time, so if you were looking at the package, you could no longer read your HTTP requests. Some features of note, it was bidirectional. For the first time, the server could send you data without you asking for it. More on that later. There's some header compression going on, so we realized that a lot of the headers that we send back and forth to our users are actually the same headers every request, because like your user agent isn't going to change in the middle of your session. So you can compress that pretty smartly, actually. There's server push, which is pushing a file from your web server to the browser cache. It doesn't actually go to your user yet, but it's there when the user needs it. It's ready for you, basically. And we had multiplexing, which solved the problem with having to wait for limited amount of connections. So HTTP2 actually only uses one connection, but they now multiplex your requests and responses onto that one connection. So you no longer had the problem where you were waiting for 6 of those long waiting requests before you could do anything else, which is very nice. And it provided a solution for domain sharding as well. All right, that seems kind of cool. How do we use it? Actually, that's the best part. It's implemented in your web browsers and in your web servers, and your web applications don't even need to change. You just need to update your web server that's serving your application, and you're using HTTP2. Or maybe you need to configure it, but besides that, you don't need to change anything. It's supported by all major browsers and all major web servers. If yours doesn't, I would argue it's not a major browser or web server. Server push is browser caches and web servers, which is a little bit strange, but it means that your user hasn't asked for the file yet, but the server sends you the file anyway because it thinks you're gonna need it. And then when you ask for it, it's in your browser cache. And browsers have the option of denying or accepting that request, basically. It's defined using a link header in your HTML. You basically add a rel preload, and then your web server will send it with the file. It will basically say, if you're asking for this HTML document, you're probably going to need this screen.css file I have over here. And it would send it first, and it looks something like this. See, at first, you would request the HTML, then you would figure out, oh, I also need the CSS for this file. So you would request the CSS, and then you get the CSS back. It's 2 round trips. But now you can request the HTML. The server can be like, oh, but you're also going to need these goodies. And then you get them in 1 round trip, which is nice. Excuse me. The multiplexing meant that server-sent events got a new life. Like I said, they had the problem of holding up your connection, and nobody else could use that connection. But because we're now multiplexing, you can use server-sent events to create sort of a stream, and you can have as many as you want, which is very nice. So you can have as many as you want on one connection, and there's no more blocking. Almost no more blocking, but we'll get to that at the end of the presentation. These new server-sent events sometimes are called reactive streams, and it's what we use for these reactive streams most of the time. The implementation is a little bit different than the chunked encoding ones we had in HTTP2, because they figured out some more cool optimizations, but the idea is the same. When you start reading about reactive streams, these are some of the terms that you get thrown at you, or reactive programming. It's asynchronous, it's resilient, it has flow control. And when I looked at this, I thought, I'm not really sure what all of this means for me as a developer. Then I looked at what's the main goal. It says to govern the exchange of stream data across an asynchronous boundary, which still didn't give me much to hold on to. So I figured I need to find a real-life example of this. So I went looking, and this is what I came up with. It's an orchestra. And I'm going to lay the terms we just saw besides the orchestra and see how they fit. So it's composable, which means you can join, you can split and merge, kind of like an orchestra. You can add members, you can remove members. It has flow control. You can ask for how much you want to be in the reactive stream. And you have a way of toggling, basically, which we're going to say more about later. But the director of an orchestra does basically that. It's message-driven. Well, in this case, music-driven, but I mean, close enough. It's resilient. If one of the orchestra members decides they don't want to play anymore, the rest of the orchestra can just go on, and it still sounds like music. Unless like half your orchestra quits, then you might have a problem. It's responsive. When the director waves the stick, everyone in the orchestra has to respond, but they do so in their own time, like when they notice, and they do. But they do have to be fast, because otherwise the music is going to sound like crap. It's elastic, which basically means they could play really softly, or like only a few members could be playing, or they could play really loud, and a bunch of the players could be playing, and it sounds like music all the time. And also, one of the analogies I like to use is this orchestra. I watch this orchestra sometimes because my mother is a choir singer, and they do backup sometimes. And these guys over here, the contrabasses, one of the contrabasses is a very static kind of expression when he plays, and the other one goes absolutely wild. And it doesn't matter how he's playing, it still sounds exactly the same, which basically elastic means doesn't matter whether it's a lot or whether it's a little bit, it works anyway. It's asynchronous, which means they all read the sheet music in their own time, and they decide when they're going to play, and they all decide when they're going to respond to the stick the director is waving, but they choose to do so when they want to. This was the hardest one to map on an orchestra, actually. Back pressure, which is basically telling the stream you're sending too much, can you slow it down a little bit? With an orchestra, it's kind of like the audience walking away because they hate your performance. Something like that, I imagine. So a little bit simplified, there are publishers, which are the musicians or the orchestra. There are subscribers, which are the listeners in the crowd. There are asynchronous streams in the middle, which is all of the music that's going on. And Reactive Streams is a collection of interfaces that helps you manage all of that. So it's kind of like the sheet music combined with the director's stick. And this picture shows you basically how it works. What I liked is that they use the volume measure for the back pressure here, which is cool with music. And then I'm going to show you how this works with Spring 5 and Reactor. But first, we need a little bit of terminology about Reactor, because they gave it some different names. Flux is a publisher. It's actually like your regular orchestra member that plays some music. A mono is a publisher, but it's a little bit of a weird one. It's like the guy in the back with the gong that hits the gong once and then stops and doesn't do anything else. So it's a publisher, but it only returns one event, and then it's done. A processor is a sort of an in-between block. It's sort of both. It can receive events, and it can pass them on to different streams. It's what you use to do stream manipulation. So if you join or you merge or you split, it's what you would use. And a subscriber is a subscriber to your orchestra, is a listener. All right, so time for a basic demo. Here you see a basic Spring Boot project with a REST controller. How many of you have used Spring Boot before, or this looks familiar? That's nice, then I don't have to explain all of that. It produces a media type text event stream value, which is your stream. We see here that the return type of this function is a flux, which is our publisher. I call it my first flux, and it lives on this endpoint. Just is a nice factory method for the flux, which lets you create a flux out of some random elements and then add a delay. So I'm going to simulate that these appear 1 second at a time. And then I did something very similar in the very easy, actually. In the JavaScript, you have an event source, which is your subscriber, basically. you can point it at the URL, and then when it receives a message, it publishes it by adding it to the inner text of my HTML document. So we're going to see it on the document in a second. And when something fails, we close the event source. So I'm going to run it. You can see it's a very basic example. And it should publish some nice values for us. Thank you. Oh, one thing I forgot to mention, HTTP2 requires you to have an HTTPS connection at all times. So here we have the application we just made. It seems like we're going to try and make an orchestra. Well, I don't know what that means yet, but if we wanted to play music, right, let's think about how would we do it. Perhaps we could send events to the crowd that were like music notes. So if we have our second flux over here, it produces the same thing, returns a flux, and it's going to try and send you music notes. And then it's going to delay those by a certain delay, because music has timing, which is very important. And then we're going to use one of the composability methods to concatenate the strings to the streams and add them together, basically. And you have a bunch of these. We're going to enable our second stream here for a second. All right. Right, so now we're receiving music. And does anyone recognize which tune this is, maybe? Yes! Actually, House of the Rising Sun. We could open a second window to see, like if we wanted an orchestra, we'd have to have multiple members. But there's a problem with these, which is if I open the page, it starts playing from the start, which means that all of you would have to open the page at the same time or this would never work to make music, basically. Or you would all be playing over each other, which is not very nice, which I hope doesn't happen. So there's a problem with these. And the difference here is that the difference between what we call a hot publisher and a cold publisher. A cold publisher will send you all the events from the start of the stream when you open it, and a hot publisher will send you only the events that arrived after you subscribed. And we can make one of those fairly easily as well. It's a little bit more complicated, but we have a stream service, which is basically a list of all our subscribers. We have the flux returning endpoint, my third flux. It still returns a text event stream value, but we have this processor in the middle right now. And it's like the in-between block. So it receives an event and it passes it on to a flux. And you can publish this processor and then it becomes a flux itself. And it will publish any event that you pass into it. And a unicast processor means it's going to cast it to one flux. So we can receive events with these unicast processor, like I said. And how do we receive events? Well, I made a simple endpoint which publishes a value, and it's going to say stream service.broadcast value. And we can look at that. It's actually still very simple, because all you do is for each processor in my list of processors, I call the onNext. So it's very much like an observer pattern, if you will. All right, let's activate that and see how it works. So now if I open the page, there's not going to be anything on it because we haven't published anything yet. And if we try to publish whatever value we want, we still need HTTPS. It should arrive here on our stream. So now we can basically tell anyone that's listening that they need to play a certain key at a certain time. And if we open a second window, over here, second subscriber, we can publish the events, and you see that they don't receive all the events that came before this, but they do receive all the new events, which is what we need for playing music. All right, so now we know how to make music. Now I figured, can we actually build that with reactive streams? So I made a web application for you to join me, and I'm going to need you to grab your phones and basically follow these instructions. So you need to have your media sound on. You need to switch to 4G internet if you can. If you can't, then that's okay. But usually, this many devices on an access point sort of kills the connection. So you're going to make a little bit less nice music. Then you're going to navigate to my website. You're going to enter your seat number with a dash and then your row should be a letter. It starts with an A from the front, and it's displayed in between the seats over there. And then you enter the room name, which is Devox, and then you hit join. I'm going to try and open it over here. I can see that a bunch of you in the back are already on this. So actually, it's seat-row. Hang on, let me put it in front. There. And then previously, when I did this presentation, I had a bunch of like notes recorded, and I would send them the same way the application did. But I figured it kind of looks like it's recorded then. So I went out and bought a keyboard and hooked it up to my laptop. And then it's sending events to the server. And I'm actually not very good pianist, so I got like pop songs for beginners. Which I'm sorry, but maybe if we have someone in the audience that plays very well, we can test it out. And you should hear, if your media sound is on, you should hear these keys. And I hear a few of you, I think. So I thought something else would be cool, is if I divide you into sections, I can kind of play you like an orchestra, so I can have part of the audience playing and part of the audience not playing. So I have these buttons on my keyboard, and when I hit them, they deactivate one of the sections, or they activate one of the sections. So I can start with seeing, well, the front row seems to be a busy section. I can see if just the front row plays. Is it actually just the front row playing? That would be bad if it isn't, right? I can have the front and the back row playing. So you see, this is a really cool way to show that it's actually reactive enough. A bunch of people still use WebSockets for these kind of things, which when you're sending from a server, it's not really necessary anymore. This is reactive enough because it's so close together that you can even make music with it. And I wanted to show that. So that's very nice that it worked. Yeah, because I programmed the... Oh, I was going to ask, is there anyone in the audience that's like a really good pianist and that wants to try? Nobody? Oh, that's too bad. Let me see if I can get the presentation back on. Right. So I actually programmed the seat numbers yesterday because I didn't know whether they would be numbered. So it's kind of exciting if it would work. And it should still, if your phone is like... if you lock your phone, it should still work, which is kind of nasty. So if you're at the party later and you still have it on, I'll try and play something. There are a few difficulties that come with using reactive streams, and I wanted you to know about those. Naming is very hard, and especially for me in Spring WebFlux, because you're dealing with publishers and subscribers and processors. And in WebFlux, they're called fluxes and monos and unicast processors. And then you have like these, if you compose a lot, like if you merge and split your streams and you apply filters to your streams, very fast you have like this middle product, which is a combination of 3 streams that do certain things. And naming that is very difficult. So watch out with that. Error handling on disconnects is kind of difficult. The room where you entered your name was actually done with reactive streams as well. And when you leave, the problem is you don't send me a notification that you're leaving. I tried doing that, but when the browser closes and it's still sending a request, it's, well, my user said I should close, so bye. And it doesn't leave you anything to react on. So what you have to do is implement something like a heartbeat. So I use the heartbeat, and every 500 milliseconds, I'm pinging your device to see if it's still there. And if it's no longer there, I disconnect you from the streams. Like I said, if you compose a lot with the streams, it very, very, very quickly becomes complexity. And you might not understand in a few years from now. So use that very sparingly and try to keep it to a minimum. Then a little bit about WebSockets. Do we still need WebSockets with this? They have a large amount of support, which basically previously you had to invent your own protocol, and it was kind of weird because you were sending binary data and it wouldn't always work. But now they have a large amount of support, and there's many libraries you can use. And if your developers already know WebSockets, then it's probably good to keep using them. If the client is sending in a lot of individual requests, it's good to use WebSockets because HTTP has headers for every request, so you have a little bit of overhead going on, and if the client is sending you a bunch of requests, it's still nice to use WebSockets. And actually, to use this, it's server-sent events, so you have to send them from a server. Like my laptop over here, I can't connect from to that from the outside world inside here. So I had to use WebSockets to send the keys to my Flux application, which WebSockets also work with Spring WebFlux, which is very nice. But I had to use WebSockets because I couldn't publish my laptop, basically. If there's large amounts of bidirectional data going on, it's still useful to use WebSockets. And if it needs to be very real-time, like I said, there's just a little bit of overhead with HTTP2. Which makes it a little bit slower, but it's actually, like you've heard, it's good enough to make music with. So, like, what application really needs to be that real time? Then looking into the future a little bit, do we still have problems? And what does HTTP3 bring for us? What we noticed with HTTP2 is that TCP gave us a few limitations. Like, it was very cool that we could send multiple requests over the single stream, like we're doing down here. But that meant if one of the packets got lost, that our window size would be halved, we would have a TCP retransmit, and all our streams would be impacted, which is not very nice. So we solved the problem of head-of-line blocking by using multiplexing here, but we created another problem of head-of-line blocking on a lower level with packet loss, basically. So Google started making the QUIC protocol actually back in 2013 already. They basically took the HTTP2 frames that we used to send over the line, and they put them onto a UDP layer, so it doesn't care about packet loss anymore. But then they put the TCP protocol on top of UDP, so you could do retransmits in UDP and still have the security that we have with TCP, which is very nice. The Internet Engineering Task Force then received the specification from Google, and they quickly decided that just using HTTP2 over QUIC wasn't enough, that it needed to support other protocols as well, maybe in the future. So they added some things to make that possible. And then that was back in 2017, maybe 2018. And then they arrived on basically using TCP over UDP to make multiple of these streams, but over a single UDP connection. So if one of your streams lost a packet, that stream would get halved and would have a retransmit going on, but none of your other streams would be impacted. The reason they chose UDP for this, which was not ideal for the solution, is that they wanted to make a new protocol, but they figured that there's so many hardware going on at the edge, like routers, firewalls, proxies, that only accept TCP and UDP, that are hard programmed to throw away all your other packets, that they basically figured they couldn't use a new protocol, so they decided to use UDP. And it is a fairly nice solution. So that's going to fix our problems, and I think the specification is coming out next June, so in a month from now. That's going to be exciting. Then a little bit about the setup. Well, I used the keyboard that I bought, which doesn't make any music on its own, actually. It's just it sends MIDI to my laptop. Then I decode the MIDI on my laptop, and I use a WebSocket to publish it to my Spring Boot application, which is in Azure, and it publishes a front end, which you all used to basically send you the reactive streams. I forgot your phones in this picture, actually. There should be a bunch of phones all around. That would be nice. Then I have some room left for questions, and I hope you like my talk. And I would ask you to please rate it in the application and leave me any feedback. Thank you. Are there any questions? Yes, I'm going to walk towards you because the room is huge.
So how does the reactive streams work, all the firewalls in between the client and the server? Are there any configuration requirements for the network?
Actually, the reactive streams just goes over HTTP2. So as long as your firewall lets through HTTP2 traffic, it's not even going to know it's a reactive stream because it's binary and it's encrypted. So it should work, yes.
How about the chunk sizes, buffers, etc., proxies? For example, if this stream becomes buffered, it will not work?
Well, it won't work as responsive, but your client supposedly wouldn't notice that it's receiving the package later.
And one last question, does the browsers also cause some kind of buffering internally?
Do the browsers do some kind of buffering internally?
Yeah.
I'm not sure, but I think so, yes. All right. Any other questions? Yes.
What about the back pressure control over HTTP?
The question is, what about back pressure control over HTTP? So I actually, with the JavaScript event source I used, I haven't found a way to do back pressure, but it is in the specification, and reactive streams are meant to link servers to each other as well. And then you can just use, which is basically called you request an amount. So when you start going over, you would, instead of still receiving the events, you would request a certain amount, and that would give you an option to say, I want this many packets next, basically. So you could slow it down from your client side. Does that make sense?
In terms of network packages or in terms of events?
In terms of events, yes. Any other questions? All right, that was it for me. Thank you all for listening, and I hope you enjoy the rest of your day.